Great. Thank you very much for having me here. And today I would like to, I'm Jiaru. I'm a PhD student of Professor Marcus Kraft. And this is a collaboration between the Como group and the Sustainable Reaction Engineering group. And today I'm going to present the title, like From Platform to Knowledge Graph, Distributed Self-Driving Laboratories. So at the start, I will introduce what is a self-driving laboratory. It's basically a fancy way of interpreting lab automation. And one way of understanding it is a closed loop of the design-make-test-analysis cycle. And normally, you start with some goal of your desired property of a molecule. And then you design the structure of that. And then you go to the lab to actually make it and then test its some properties. And then you analyze to learn what you have, basically to learn from your previous experiment. And then you basically iterate this loop. So that in theory should accelerate the research process. And many successful implementations are out there. So people start to think big. And how we can actually connect the different laboratories together to make a network of them. And so that we can reach the tipping point to really accelerate the scientific adventures. So in a recent community perspective, it is projected that over the next 15 years, we will reach the tipping point to have a globally integrated network. And more recently, NASA even proposed that, all the labs on the Earth is not enough. We need to connect this to the labs in the space so that we can support the human exploration in the deeper space. But we argue that, yeah, the visions are all great, but if we want to actually do that, there's challenges in scaling. So the first one is like how you can orchestrate the heterogeneous resources. So because if you think about this, each different lab, they will have their favorite hardware vendors. They will have their favorite softwares. So how we can actually connect these bits and pieces together. And more importantly, like once you have done your experiment, how the data can actually be shared in a common language so that they are not like one guy is doing this in a CSV file, another one is doing it in a database. So that's basically non-interoperable. And also, we want to make sure that everything is fair so that we have a record of what exactly was done step by step. So that can be basically reproduced in other group. So this really reinforces the robustness of the scientific discoveries. And hopefully with this work, we would like to show some proof of concept to address these challenges. So as you may aware, Cambridge have an overseas research institute in Singapore that's called Cambridge Cares. And there's a lab that has a setup of the flow chemistry setup. There's a sort of similar but not identical setup in the Cambridge site, the IDMT. And each of these are managed by one of those team members, Dongjiang and Connor. So the problem is like how we can actually connect these two. So the first thing we do is we want to take the abstraction. So what are the data, what are the software, what are the hardware that's involved in the process, and how we can streamline the workflow within this. So as I mentioned, that's the DMTA cycles. So here you can see that you can have your favorite design of experiment algorithm to actually propose the next condition. And then you can have some scheduler. So to actually find the suitable lab to actually do this experiment. And then so that goes into the lab space. And then you basically have the sort of digital twin of the lab, of the hardware, so that you can actually invoke the experiment. And then that will basically send back the results. And then you can have that analysis, so on and so forth. So the integration, so basically these integration proposes that we have the data, the software, the hardware, and the workflow all in one place. But the problem is how we can do that. And next, I would like to introduce the approach we're taking. That's basically the URL avatar. It is a dynamic knowledge graph-based digital twin that has a super ambitious aim that to capture everything that can potentially be conceptualized in the real world. So we want to have a living copy of the real world in the digital space. So the center of this, this vision is that we have the ontologies. So ontologies captures the concept and relationships, and they provide the context for the things that we're doing. And then with these ontologies, we can basically instantiate the digital twin of the hardware, basically the lab, into the knowledge graph. And then on top of that, we can have the agents that as the executable knowledge components that they actually autonomously act on the knowledge graph to restructure the graph as the time elapses. So hopefully, with this technology, we will be able to connect the labs that are geographically apart. So, and with that vision, the first step is to identify what are the work that needs to be done on the ontology side for the data representation. So previously, we had done a review paper that we analyzed what are the current community efforts in the data representation and exchange in the laboratory automation. And then we basically identified that there's actually quite a big gap in the semantic side that the ontology needs to be developed for the analytical data method and the procedure and also the holistic workflow side. And based on that, this is a snapshot of the ontologies that we developed. So when you think about the iterative cycle of the DMTA, you normally start with the research goals. So what are the properties that you want to actually optimize? And for that, there will be like the conceptual description of the chemical reaction. And then you also need the design of experiment and the concrete reaction experiment that actually represent the things that you have done in the lab. And of course, you need to have the digital twin representation for the laboratory. So there's also concept there. But the beauty of the knowledge graph is that they are all connected. So we're actually bringing the knowledge from different domains in the one place. And with that, we can basically instantiate the things that we know in the lab. And then, so at the bottom here, you can see that these are actually a snapshot of the triples, that the things actually exist in the knowledge graph. And then based on top of that, you can basically pull the information to extract basically the information that will be interest to different roles. For example, for the chemists, they will be more interested in what actually is the reaction, what are the species information properties. And for the data scientists, they probably just care about like the, they are more care about the statistical side of the things. And for the lab manager, they would like to know actually what's happening in the lab and to see what are the status of the equipment and if there's any action needs to be done. And with this, hopefully, that we think we have addressed the problem of data representation in a common language. And so the next step is to talk about the agent. So here we employed something called derived information framework. So it is a knowledge graph native solution that we developed initially for enable interoperability in the smart cities domain. But then as we are developing it, we figure out, yeah, it's actually quite generic, and we can use it to streamline the workflow in a lab as well. So basically, the central idea here is that we have the information you are generating in an experiment is actually kind of derived information that derived from some sort of your input. That can be your input of the parameters that you set to the instrument, or that can be input of basically the historical data you're using for the DOE analysis. And then the results will be basically the derived information, and then we mark up this process as something called derivation, and then this thing can be done by an agent. So that was one process, and then if there's multiple such similar process arise, and then we basically form a directed acyclic graph. So within this, at any point in the graph, you can actually trace that what are the source information that was affecting that the information that you have at the moment. And then in another direction, that's the information flow direction, you can basically see that what's happening here that will have like ripple effect to all the other information that exists in a graph. So, and with that, we draw out the, again, this is a snapshot of what's happening in the knowledge graph, that the agents get chained together with these sort of like the derivations, and then they basically streamline the workflow. And with this, hopefully we have solved the problem of orchestration. So, yeah, with that tools, we would like to apply this to proof of concept chemistry. And this chemistry we selected is easy enough. So that's the aldol condensation reaction between benzaldehyde and acetone. And here we have 4 parameters that we're optimizing. The molar equivalence ratio of the acetone of the catalyst, and the residence time, and the reaction temperature. And so this is the connectivity of the hardware, and this one shows the one in Singapore. That is, all the chemicals are sourced by the pumps. But then the one we have in basically sourced by the pumps connected with the reagent bottles. But the one we have in Cambridge, actually, we use auto sampler to source the chemicals. And with that, so the whole knowledge graph thing happens, all start with kind of prompt or the information that provided by the scientist to the agent. So, so here we're saying like, yeah, we want to optimize the reaction condition of this reaction with benzaldehyde and acetone. And here's the target cost for this product, and here's the target yield. And we give the agents a week or like in total 100 experiments. And can you actually find the Pareto front with the 2 setup? So what the agent does is that it parses the information, and then it translates the instruction from the scientist to a machine-readable format, so that it basically instantiates that information into the knowledge graph. So as I mentioned, that we have the derived information framework that manages the knowledge graph. So it's like you're dropping a stone in the river or in a lake, and then there's a ripple effect. So basically, information propagates in the knowledge graph. And then here that it basically invokes the whole iterative process. So as I mentioned, there's the design of experiment, execution, and analysis, so on and so forth. And then once that's done, then the goal agent actually evaluates if the current process meets the goal or not. And then it also have access to know like what are the current resources limitations, like and what's basically track the progress. And so these two are iterative loop, and then it continues until either we used up the resources or the goal are met. And with that, I would like to show the results that we have here. And so the 2 objectives are yield and the cost, as I mentioned. And so you can see here that we have this Pareto front. And the blue points are experiments done in Cambridge side. The orange is done in the Singapore side. And on the right side, that's the parameter space. And the size of the dots there actually is the equivalence ratio of the catalyst. And I also mentioned we'd like to capture the fair provenance. So I would like to show that what this actually means when I say fair provenance. So this is the iterative, interactive animation that we retracted from the records made in the knowledge graph. So within this, you can see the bottom, the slider, that's the actual timestamp of the events happens. And then we can see that as the time goes by, where actually the 2 labs are sharing the data, then they're pushing the Pareto front of this optimization problem. And I hope you have noticed that when the mouse is on top of the node, there was a pop-up window, so basically shows all the other information that you can get from the knowledge graph. And one interesting bit is after we start the experiment for like 10 hours, and then there will actually hardware failure in the Singapore side, and then that triggers an automated email sent to the basically the developer and saying, yeah, this is there's actually something went wrong, and then we need to take out this equipment. So basically that was we basically take it out of the campaign, and then the Cambridge side carried over and finished the campaign. Basically, this is why you see there's like unbalanced orange and blue dots in the left side. So hopefully with this, this is convincing enough that you can see that we address the fair provenance problem. And finally, I would like to bring you to a slightly bigger context of the whatever project that is beyond merely automated experiment. So here we can see that our beautiful home Earth. And we'll soon zoom into the Singapore, and you can actually see Maria Bay at the bottom. And then if we keep going inside, we will hopefully reach the Create building. That's where the Singapore lab sits. Yep, it's there. And yes, so you can see that this is actually a beam representation of the lab, and that's actually also within the knowledge graph. And here you can see there's a couple of fume hood. And yep, this is actually the robot that we're using in this work from the Singapore side. And so, yes. With that, I would like to summarize my talk. So hopefully I have convinced you that the What Avatar enables the interoperability between different equipment and also the data. And all the data are actually captured following FAIR principles, so you can retrack what's actually happened in the past. And our framework enabled this real-time collaboration between the two labs that across like more than 10,000 kilometers away. And we actually hope that our work will spark the start of like our path towards a globally connected research network. And with that, I would like to acknowledge all the co-authors of this work that made amazing contributions, and all the people from Como Group and the SRE Group for the helpful discussions and moral support, and all the funding bodies to make this happen, and all the audience for your attention. And I have put the QR code to our preprint on the top, so you can feel free to have a look. And please do reach out if you're interested for collaboration. Thank you very much.